Hello everyone, welcome to channel once again with new topic. Today we're diving into this explainer to demystify the virtual private cloud, or VPC. Even for seasoned tech pros, looking at cloud networking diagrams can feel like staring at a giant bowl of tangled spaghetti, right? Well, we're going to completely untangle that complexity by mapping this whole architecture to something you already know and understand perfectly.
So, why exactly is the virtual private cloud the most feared topic in cloud computing? Honestly, it's just the sheer volume of moving parts. You've got route tables, gateways, subnets, all seemingly stacked on top of each other. But listen, if we just strip away all that intimidating technical jargon, you'll actually see it's one of the most elegantly organized systems in the world.
To really get the why behind the VPC, we kind of have to rewind a bit. Over a decade ago, companies were desperate to scale up fast, but they absolutely loathed the physical hassle of it all. Racking servers, managing massive cooling systems, dealing with broken hardware. It was just incredibly slow and painfully expensive. So AWS steps in as the ultimate digital landlord. They essentially said, hey, we'll handle the physical real estate, you just rent the virtual space. A total game changer, right?
Fast forward to around 2013, and everyone from tiny startups to massive enterprises was renting out these virtual machines to save money. But there was a terrifying catch: the shared server problem. AWS was literally putting virtual machines from totally different companies onto the exact same physical server. Meaning, if a hacker managed to breach just one poorly secured startup, they were suddenly inside that physical box, sitting right next door to your highly sensitive enterprise data. It was basically a ticking time bomb for privacy.
Enter the virtual private cloud. This is where absolutely everything changes. To fix that shared server crisis, AWS stopped putting everyone in one massive open digital field and instead allowed you to build your own secure, gated community. It works exactly like a physical gated neighborhood. You get strict digital property lines, a heavily guarded main gate, and a completely impenetrable guest list.
Now, when DevOps engineers actually construct this community from the ground up, they don't buy acres of land, obviously. They claim a massive IP address block. This gives them up to 65,000 unique addresses to build on. Then they carve that massive digital plot of land into smaller, dedicated project plots. And finally, they erect their servers. Think of those as the digital houses, right inside those specific, controlled boundaries.
And you definitely wouldn't just throw all your servers into one chaotic bucket. Your highly sensitive payments database shouldn't just be mingling with your public-facing web servers. That's where a subnet comes into play. A subnet simply lets you take that massive pool of IP addresses and divide it into strictly isolated, dedicated neighborhoods. This ensures that a breach in one single area doesn't automatically spell disaster for the whole shebang.
Of course, building a fancy gated community is utterly useless if no one can actually come visit, right? Enter the Internet Gateway. Now, this isn't just a regular door. It is the absolute mandatory primary entry point for your cloud. Without an Internet Gateway attached to your network, your cloud resources might as well be stranded on a deserted island. It is the ultimate vital gatekeeper for anyone coming from the public web. Okay, so a visitor passes through that main gate. But how do they actually know where to go next? Well, that's exactly what the route table is for. It acts as the ultimate digital street map. It provides a very strict set of directions that dictates the precise path incoming traffic absolutely must take to navigate from the public gateway all the way down to the correct internal subnet.
So we've got all our structural defenses perfectly in place, but how do they actually work together in real time? Let's zoom in. Imagine you're at home, typing a URL into your browser. How does your solitary little data packet actually survive the maze of this heavily guarded cloud city to fetch your data? Let's track it.
Here is the exact fast-paced journey. First, the request leaves your laptop. Second, it hits that internet gateway we talked about. Third, it enters a public subnet where it's immediately greeted by a load balancer, which is kind of like a traffic cop checking server capacity. Fourth, that load balancer checks the route table for precise turn-by-turn directions. Fifth, right before it can enter the server, it bounces against a security group. This is a strict checkpoint verifying your exact IP and port number. And finally, step 6. The packet clears security and reaches your private application.
Isn't that just a beautifully orchestrated gauntlet? Every AWS component perfectly mirrors our physical community defenses, from the gateway acting as the community entry pass all the way down to the security group bouncers at the actual server level. We even have things called NACLs, Network Access Control Lists, which essentially act as an automated neighborhood watch, protecting the entire subnet at an even higher architectural level.
But wait, now we arrive at a truly fascinating paradox. We know external traffic can't easily waltz into a private subnet, but those hidden, isolated servers still need vital software patches from the open internet, right? If a private server reaches out to the web directly, it exposes its private IP address. And in today's threat landscape, an exposed IP is scanned and targeted by malicious bots in literally minutes. So how on earth do we update safely?
The brilliant workaround here is the NAT gateway. Think of it as the ultimate master of disguise. It sits out in the public subnet and acts as a highly secure proxy. When your private server desperately needs an update, it just hands the request to the NAT gateway. The gateway then goes out to the public internet, securely grabs the download, and completely masks your private server's true identity from the outside world. It's genius. Finally, how do you actually prove all this is secure? To keep a watchful eye on all this fascinating invisible traffic, you simply activate VPC flow logs. These are basically the ultimate security cameras of your network, quietly recording every single accepted and dropped packet. So there you have it. You now understand the logical map of the cloud's gated community, and any fear of cloud networking should be completely gone. But here's a thought to leave you with as we wrap up this explainer. As hackers get smarter and remote work completely decentralizes everything we do, is the rigid boundary of a VPC still enough? Or is it merely the first line of defense in a brand new zero-trust world?